Hey everyone, Mr. Donzi here. I'm going to go ahead and make some instructional videos to try to get this information out to you. And we're going to start with chapter 6, and this is the first one, 6.1, graphing exponential functions. Now you may be wondering, what is an exponential function? I'm going to start off with an example. Say you found an extremely funny TikTok video and you needed to share it with two of your closest friends. And then those two friends shared it with two of their closest friends, and that pattern continues. Here's what that pattern would look like. You have you yourself, the two friends you shared it with, the two friends that they shared it with, and again, you see that this pattern grows extremely fast. I'm going to take that information that we have from this tree and I'm going to turn it into a table. I start with 0 because we didn't share it with anyone yet, and it has one view. Then we have our first share, has 3 total views. The second share ends up with 7 total views. And then finally, 3 shares with a total of 15 views. Now, a table is essentially a collection of ordered pairs, so I can take those ordered pairs and I can graph them. Here's what this graph looks like. That's an exponential function. Now let's be a little more formal about that. An exponential function is a function where the variable is in the exponent and can be written in the following form. F of x is equal to a times b to the x plus or minus h power plus or minus k. Each one of those letters has a particular meaning. Let's start with a. It says the absolute value of a is greater than 1. That just means that whether the number is positive or it's negative, as long as it's bigger than 1, that graph is going to stretch vertically by a factor of a. Whereas if that number is between 0 and 1, fraction, or a decimal, that graph is going to compress vertically by a factor of a. And finally, if a is negative, that graph is going to reflect over the x-axis. Instead of going up, it will now face down. The next letter we have, b. B stands for the base, and we're going to use that number to find these 3 ordered pairs every time that we start graphing. That's negative 1, 1 over b, 0, 1, 1 comma b. Next letter is h. H stands for horizontal, so if the exponent says x minus h, the graph is going to move right h times. If the exponent says x plus h, the graph is going to move left h times. So you may remember that from some of our other transformations. We would always go the opposite direction. The last letter we have is k. If k is positive, graph moves up k times. If the graph is negative, it's going to move down k times. So again, just like our other transformations, you go with the number, up or down. One thing that is new, k is also going to be known as our horizontal asymptote and the number for the range. Now you may be wondering, what is a horizontal asymptote? An asymptote in general is a line where the graph gets extremely close to, but it's never going to cross it. So now let's use all that information and graph an example. So we got y equals 2 to the x power plus 1. Step 1, and I'm going to use this every time, is I'm going to use the letter k, or the number that's in the k position, for my horizontal asymptote. So the number I have here is a 1. That means I draw a horizontal line that crosses through the y-axis at positive 1. So the graph will not cross this line. Step 2, I'm going to find my 3 base ordered pairs. The base in this case is the 2. So as I plug that information in, I have negative 1, 1 half, 0, 1, 1, comma 2. Step 3, if necessary, so you may not have to do this every time, multiply my y values in the ordered pairs by a, then add or subtract k. Now I do not have an a value because there is not a number to the left of the 2 or in front of it, but I do, however, have a number in the k position. It's the plus 1. So I'm going to add a 1 to all of those y values in my ordered pairs. So 1 half gets bumped up to 1 and 1 half. 1 gets bumped up to 2, and 2 gets bumped up to 3. Step 4, another if necessary step, add or subtract to the x values the h number. I look at my exponent because that's where the h is at. I don't see a number there, so it technically means there's a plus 0. So if I add 0 to all of my x values, that's not going to change the numbers. So there are my 3 final ordered pairs. Step 5, plot the points and draw the graph. So I go ahead and plot those ordered pairs, draw the graph. Here's what 2 to the x power plus 1 looks like. Now stating the domain and the range. You may remember we had pencil tests that we would use for the domain. I'd have a vertical line that would cross through the x-axis, and I would see how, is there a point when it's not touching the line? I move. Even though it looks like to the right there that it's not touching the graph, this graph does go on forever to the right, so it's always touching the vertical line, which means my domain will be all real numbers. Check the range. As I work up, my line will not start touching the graph until I get to that horizontal asymptote, and then finally it does start touching the graph. So at what point does it start touching it? It looks like 1, but again, the horizontal asymptote means that the graph doesn't actually cross it, so I'm strictly above 1, so my range will be y values that are greater than 1. These are the 5 steps that I will always use to graph an exponential function. There are 2 different types of exponential functions. The first type, the one that we just graphed, exponential growth. That graph will always go up from left to right in this fashion. And that always occurs when your base is greater than 1. So as soon as you see a base bigger than 1, you automatically know that we have an exponential growth. We also have exponential decay, where the graph goes down from left to right. That occurs when my base is between 0 and 1. Most of the time you're going to see your base written as a fraction, but it also could be a decimal. So now let's graph an example that's exponential decay. Now if you look at my base, 1/4, that is a fraction. It's between 0 and 1. So I know that the graph is going to go down from left to right. But I'll follow those same 5 steps that I went through previously. Step 1, I have a horizontal asymptote at -2. So I draw the horizontal line, crosses the y-axis at -2. Step 2, find 3 base ordered pairs. My base in this case is 1/4. So I start with my base ordered pairs. -1, 1 over 1/4, 0, 1, 1, 1/4. Now the 1 over 1/4 does look a little weird, but if you remember that dividing by a fraction would be the same thing as multiplying by the reciprocal. So that ordered pair is technically -1/4. Step 3, multiply my y values by 2. Now you might notice that I have a 2 in my A position of the exponential function. After I multiply by 2, then I'm going to subtract by 2 because of the -2 in the K position. I apply those changes. Those numbers now change to -1/6, 0, 0, 1, -1.5. Step 4, subtract 2 from each of my x values. Where am I getting that to? The exponent. Always the opposite, so the opposite of +2 is -2. I subtract 2 from my x values. I have my final 3 ordered pairs, -3, 6, -2, 0, -1, -1.5. The last step is to plot them and draw the graph. So here's the plots, the graph, there's your exponential decay. I'm going to check my domain. Got my vertical line I worked through. It will always be touching the graph. So once again, just like my exponential growth, domain is going to be all real numbers. I go in to check the range. I'm working up. Doesn't start touching it until I get the horizontal asymptote, or just past the horizontal asymptote, which means my y values are greater than, strictly greater than, -2. Applications of exponential functions. We have 2 applications that we're going to talk about. We have the growth factor and we have decay factor. If you look at the 2 formulas, they are very, very similar. The one different, growth. Growth means getting bigger, which would be related to sum. Decay, meaning smaller, which would be related to the difference. Each piece of those functions has a particular meaning, the ones that I have in color and the A of t. A of t represents your future value. A represents the starting value. R represents the rate, but particularly your rate as a decimal value. And T, time. So say you have a cup of green tea. It contains 35 milligrams of caffeine. The average person can eliminate approximately 12.5% of caffeine from their system per hour. We're going to write an exponential function that represents this situation. Now we've got two situations. We've got growth factor, we have decay factor. But if I read the words, the word eliminate suggests decay. So I'm going to use the decay factor formula. We started with 35 milligrams of caffeine in the cup. So my starting value will be 35. There was a percent mentioned. That's not in decimal form, even though there is a decimal there. I still have to divide it by the 100 decimal, or the 100% possible, to get a new decimal value of 0.125. I will take that information, I plug it into the decay factor formula. I see that I can simplify 1 minus 0.125 and turn that in to 0.875. That is my formula, or my exponential function, that represents this situation. A of t equals 35 times 0.875 to the t power. Next thing that we're going to look at is how much caffeine would be left in the body after 2 hours. 2 hours suggests the time, so where I have t's in the function, I'm going to replace them with the 2, follow my order of operations, and find out that after 2 hours, there's approximately 26.8 milligrams of caffeine left in the body. So that's everything as far as graphing exponential functions and applying exponential functions.